For example, let's say we take a function such as x to the fourth minus 2x squared plus 3, something like that. And we want to find the maximum and minimum values. Find the local extrema of f, if it has any. All right, so we see that according to the first derivative test, the local extrema are totally linked to where the derivative is positive or negative, and where the derivative is 0 or undefined, i.e. to critical values, and to the first derivative sign, as we mentioned for increasing and decreasing a moment ago, irrespectively. So we need to find the derivative, hence first derivative test, and we'll have 4x cubed minus 4x. Again, to find where the first derivative is positive or negative, just like the previous example, right, this is just the very next small step from the previous example. Because once you've found where the function is increasing and decreasing, it's not a big leap to figure out where it has relative extrema. So we'll set this equal to 0 in an attempt to actually solve, all right, the inequalities greater than 0 and less than 0 for this derivative. Right? We know that setting equal to 0 will help. It will help determine the sign of the derivative in every place else. So we have factored 4x away, and we'll end up with x squared minus 1, which we can also factor again since it's the difference of squares. We'll have 4x, x minus 1, x plus 1. And now we're going to do what I did a minute ago just to find where it was increasing and decreasing. We're going to make a sign chart. The difference is with this example, we will just make, like I said, one extra leap here and claim where the function has relative extrema. But finding where the function is increasing and decreasing is paramount to finding the solution to the whole. So we have 3 critical values, 0, 1, and -1, one for each of these factors. There's our critical values. I'm going to plot them on this number line. And again, this is an x-axis really. Right? Don't need the y-axis for these situations. There's the x-axis. Again, without scale, 0, -1, and 1. Just get a proper order. So now we just need to figure out the sign on each of these 4 subintervals. Right? So I'm also going to explain now how you can figure out the sign without going through as many test cases. So one important rule to realize is when all of the factors are to the first power, you might say. Another way of saying that is all the roots here are multiplicity 1. Okay? If all the roots are multiplicity 1, and not even multiplicity 1, but multiplicity odd, right? So if this had been x to the third, I'd have the same situation I'm about to explain. Okay? So if all the factors are to the first power, that is, all of the roots are multiplicity 1, and then you can extrapolate from that also, if they're just odd, right, that the multiplicity is odd, then I only need to find one sign of the derivative in here for one of these intervals, and I will know the rest because the signs across this sign chart will have to alternate, for sure. They did that in the last example. I just didn't explain this property there, but it's very useful because it just eases up how many calculations you have to do. So for instance, I'll just take a test case from way over here. It doesn't really matter. A lot of times you don't even have to take a number. For example, I'm just going to test a large positive number from over here, right? Just test any large positive just to show you that it doesn't really matter about the particulars. If I take a super large positive number here, right, and I plug it in for x, certainly you can tell that all of the factors would be positive, right? -1's not going to outweigh that very large positive number. And here it's the number itself, and here I'm just adding 1. So it's pretty clear that all the factors will be positive, and the 4 here is already positive. So if that's the case, then that means the first derivative, right, sign would be positive here. And then since each of these is only to a power which is 1, which is the case a lot in a lot of these problems. But again, you could say even if they were all power 3 or 5 or whatever, it wouldn't matter as long as it's an odd power. Then I can automatically fill in the rest of the chart without doing any more test cases, which is extremely useful and efficient. Okay. All right, so now we know that the function is decreasing from negative infinity to -1. I'm not going to write out all the intervals right here, but you can just say them out. From -1 to 0, the function is increasing. From 0 to 1, it's decreasing. And from 1 to infinity, the function is increasing back again. But we're supposed to find the local extrema. Okay, so no big deal. Since I know that at -1, 0, and 1, the derivative went to 0, right? The derivative went through a horizontal tangent, right? And we see that there are sign changes at every one of these critical values in our sign chart. There is a sign change every single time. So therefore, again, without memorizing a verbal rule, let's just look at what happens. If the derivative is 0 here, but the derivative is negative going to positive, right, changing right at this location, that means the function was going down in a sense, and then it started going up afterwards, because that's what the first derivative implies back to the original function. If the first derivative is negative, the original function is decreasing. If the first derivative is positive, the original function is increasing. So the original function f, which is really what we're concerned about, was going down, went through a horizontal tangent here, and then went back up again. So therefore, -1 is the place where we have a local minimum. So we have a local minimum at x equals -1. But the same would hold true over here at 1, right? It looks like the derivative is negative and then positive, so the derivative changed sign, specifically from negative to positive, so therefore 1 is the location of a local min. You have a local max happening at 0 for the opposite reason. Because the first derivative was positive, right, it's going up, goes to a horizontal tangent right at 0. And then the derivative goes negative, implying the function goes down after the fact. Therefore, you must have passed through a local maximum at x equals 0. So now all you would do to find the local max and min, right, would be to plug these numbers back into the original function and see what you get. So when I plug in -1, we'll get 1 minus 2 plus 3. That's 0. 0. It's 2. And when I plug in 1, I'll get the same thing. So I get 2 again. When I plug in 0, we get 3. Okay. So now I have the location, -1, 1, and 0 of the local extrema, and I also know the values of the local extrema of 2 and 3. So again, this was relative or local mins, and this was a relative max. And we have the answer to the problem.